Okay, let me just make sure that we are live so we can start. Yes, we are. Okay, so good afternoon, everyone. Welcome to Valongo Seminars. And today we have the great pleasure to have as our guest Dr. Ann Hornschemeier. And I'll just make a quick introduction. So Dr. Ann Hornschemeier specializes in studies of X-ray emission from accreting black hole and neutron star binary populations, both in the local universe and at cosmologically interesting distances. And this work is carried out using surveys by space-based X-ray, UV, and infrared observatories, as well as ground-based telescopes working in coordination with theories. She chairs the Nustar Starburst and Local Group Science Working Group, coordinating observations with Chandra, XMM Newton, and Swift. Dr. Hornschemeier currently serves as the chief of the X-ray Astrophysics Laboratory at NASA Goddard Space Flight Center, and is personally also heavily involved in future missions, serving as the only US science co-eye on the Wide Field Imager instrument on the European Space Agency's Athena X-ray Observatory, and also as a member of the International Consortium for the Laser Interferometer Space Antenna, LISA mission, a space-based gravitational wave mission led by ESA. So you are here with Luan Ghezi. I'm the organizer of the Valongo Seminars. We also have Douglas and Ariana in the background. And I'll leave the floor to our speaker, Dr. Ann Hornschemeier. So Ann, thank you very much for accepting our invitation. It's a great pleasure to have you here today.
All right. Thank you, Luan, for such a nice welcome, such a warm welcome. I am, of course, sorry that I'm not in Brazil. I've put a URL in the private chat window, which I might ask Luan or someone to copy into the comments field, because that will be very helpful to our participants. This talk is going to involve some interaction. So I hope you have a computer, or you're probably on a computer right now, but a web browser handy, or a cell phone will work. You can respond to your cell phone. I'm going to be asking questions during the talk. So just to get people ready for that, the URL is being put in the comments field. Okay, so without further ado, I'm Ann Hornschemeier Cardiff. I put my photo on the opening slide because we cannot see each other's faces like we would during a normal colloquium, and I thought it might help you to have a slightly better view of what I look like. I want to thank my colleague, Professor Julia de Mello at Catholic University. She's the vice provost there, for providing Portuguese subtitles. So on most of my slides, you will find Portuguese subtitles, not on the question slides. But anyway, we're going to talk about current frontiers in X-ray astronomy, hard X-ray studies, and X-ray all-sky surveys. What really unifies these is that we can make great scientific progress with modest amount of money for missions. So these are studies that we can conduct with medium and small scale sorts of missions. Okay, so we're going to get started with the interactive portion of our talk. I've got an iPad up, so you're going to see me going back and forth a little bit if you see my picture. So I recommend, there are two options at the top of the slide, but I recommend that you follow the URL, which should be in the comment field. So polev.com/AnnHornschem074. And by the way, keep your web browser open, because as we go through this talk, we will find that the question will update in your browser. So if you just keep it open, then you're going to be ready. Okay. So I'm going to give everybody a moment, especially since this is our first one. All right. So you can see the responses on the screen. All right, I see we're up to half a dozen responses so far. Okay, giving people a chance. Okay, we've got a couple more coming in. And I appreciate the honesty. Who said I was awake right now? So we've got at least one extremely honest person. I'm sure everybody's being honest about what time they got up. Okay, so this was really just a test case to make sure that we got our tool working here. So the next question is a little more serious. So keep your web browser open because it's going to update. And there's a little bit of an internet time lag. So it may take a moment for the question on my screen to show up on your screen. But go ahead. You might have to reload it. There we go. We got one person that's already got. So how familiar are you with X-ray optics? And it goes from the top as expert. I know all about it. Somewhat familiar. I know a little bit, but not much. I don't know about X-ray optics at all. Give people a chance to reply. Okay. All right. And it's interesting that I'm seeing more responses now total. So I think people are getting into the swing of this. So again, there's a couple options here. I do recommend the URL pullev.com/Hornschem074 because you can just keep the browser open. Okay. I think that we have adequately tested our interactive mode here. Okay. So we've got people who know a little bit or somewhat familiar, and at least some people that don't know about X-ray optics. Okay, that's why I decided to spend a little bit of time going over this. Okay, so I'm going to move on. There will be more questions coming. And by the way, let me give you one more reminder that at the end of the talk, I'm going to ask you what your favorite part of the talk was. So you can be ready to type something into the URL at the end of the talk. But it's, I think, kinder to let you know that it's coming. So you should pick something from the talk that you want to respond at the end. Okay, so now we're going to move on. So this is an X-ray astronomy talk. First part will be to talk about Chandra and Nustar. I hope you are familiar with the Chandra X-ray Observatory, but Nustar is a hard X-ray observatory that operates above 10 kiloelectron volts. So we'll have a quick primer on X-ray optics because it sounds like that's a good idea. And then we're going to talk about luminous black holes and pulsars in nearby starburst galaxies, as well as the spectral energy distribution of galaxies. So, and then after that, we will switch gears and we're going to talk about wide field surveys in the X-rays. And this is very exciting because the eROSITA experiment on board the Spectrum Röntgen Gamma mission has just launched last year, July 2019. So we're at an interesting moment in history where we have an all-sky X-ray survey that's going on right now. And I'm going to be talking about the future in both of these areas, future missions. Okay, so first off, extragalactic X-ray binaries from 0.5 to 30 keV with Chandra and Nustar. And of course, I mentioned Portuguese subtitles on my slides. So I could see there's a little bit of text wraparound for M83 and M82 here. But mostly what we're doing with Nustar, which is the first truly imaging hard X-ray telescope, has a 20 arcsecond center to its point spread function, 50 arcseconds total beam. So that really restricts us to relatively nearby galaxies. We don't have Hubble quality to be able to look at very distant galaxies. So many of the galaxies we study are famous ones, like the ones you see here, M83, M82, ARP299, relatively nearby galaxies. So Chandra and Nustar we use together because they provide us exquisite imaging from softer X-ray energies all the way up to harder X-ray energies. So I'm starting off with a little bit of introduction about X-ray emission from galaxies before I get into the optics part. So the X-ray emission from most normal galaxies is dominated by accreting binaries. So binary star systems where you've got a compact object and it's accreting from some other type of star, and the hot interstellar medium. So an excellent example of a normal galaxy is, of course, our own Milky Way. So, and when we say normal galaxy, generally we mean one that is not dominated by a supermassive black hole. And so I like to show this plot from Bodaji et al. 2012, which all these little points here, the blue circles are OB associations, and the red diamonds are high mass X-ray binary systems, where there is a high mass, like an O or B star, with material being accreted onto a black hole or a neutron star. And you can sort of see, this is our location in the galaxy. Hopefully you can see my cursor. And you can see that the high mass X-ray binaries trace along the spiral arms of the galaxy. And these are all the X-ray point sources that are above about 10 to the 38 ergs per second. Don't worry too much about that number, but it's a good orientation point for you. The total X-ray luminosity over Milky Way is 6 times 10 to the 39 ergs per second in this band, 0.5 to 8 keV. But at any given point, one of these X-ray binaries may pop up and be the brightest source in the galaxy. So this is a distant galaxy detected with Chandra. This is a Hubble image, and we see that one individual bright X-ray source dominates the X-ray emission of the galaxy. And this single X-ray source is about 10 to the 39 ergs per second. So these are the types of systems we're talking about. So why should we study the X-ray emission from galaxies? Well, we can get at star formation in heavily obscured areas because X-rays pierce through obscuring material. The accreting binaries themselves, the neutron stars and black holes, give us an independent probe of star formation, the initial mass function, and that emission persists for a very long time. So you can sort of think of neutron stars and black holes as being, the dead bodies left over after a star formation episode. So after stellar birth and stellar life is stellar death. So we can find these neutron stars and black holes and learn about what happened in the past in these galaxies. We can also study the hot gas in these galaxies to learn about the interstellar medium, which is very important for galaxy evolution. I'm not going to be talking about hot gas nearly as much today. So now we'll get to a quick primer on X-ray optics and why we go to even harder energies above 10 keV. Okay, so X-ray optics are based on grazing incidence. So hopefully you can see my cursor. Okay, so you can see the light actually skips over the surface of the X-ray shells and then goes many meters down to the detectors that are at the focal plane. And this is an example of the Chandra X-ray mirrors that operate at 0.5 to 10 keV. For your reference, Chandra has only 4 X-ray mirror shells, 4 exquisite, nearly perfect mirror shells that were figured and polished to achieve very good angular resolution of less than an arc second, more like half an arc second on axis angular resolution. But they were very expensive and very heavy. And again, the X-rays skip over the surface and get reflected down here at the focal plane. So this is typically how we get the best angular resolution in the X-rays. And it's very similar to the conic sections that are used in, it's identical to the conic sections that are used in optical and infrared astronomy and other fields. We just use the outer part of the conic section, the paraboloid and hyperboloid. We take we rotate the paraboloid and hyperboloid to provide shells. So the Nustar X-ray optics were produced in collaboration between Goddard, where I work in Maryland, and JPL out in California. And there were 3,000 pieces of glass corresponding to these hyperboloid and paraboloid surfaces that were produced at Goddard. And this is my colleague, Will Zhang, who produced these pieces of glass. So what we were able to do then is to produce a grazing incidence optic that operates at energies above 10 keV. We put coatings on the optics to improve their reflectivity, multi-layer coatings. I'm not going to go over that right now. But before Nustar operated, all hard X-ray optics before this, there had been hard X-ray missions. Nustar is not the first mission to operate above 10 keV. But the previous missions, like Integral and Swift-BAT being excellent examples, used something called coated masks. So you basically had a punched out pattern in a plate, and then you would infer based on the pattern on the detector where the astronomical source was. This provides more like degree or many tens of arc minutes positional accuracy. Whereas with grazing incidence optics, we can get arc second level. Now, Nustar is the first ever imaging hard X-ray telescope. So as I said, the center of the beam is 20 arc seconds, and the full extent, full width half maximum, is closer to, it's in the 50s of arc seconds. Okay. But this is notable. So this is what the Nustar optics look like. So we actually take many of those paraboloid and hyperboloid shells. You can see the demarcation line between the primary and secondary hyperboloid and paraboloid optics. And you can see all the X-ray mirror shells packed in together so that when you're looking down the X-ray optic, you have as much collecting area as possible at hard X-rays. And this is what the collecting area looks like. And I just want to warn you that we have a question coming up next, so make sure you've got your web browser available. So Chandra ACIS has the best angular resolution right now of any X-ray observatory. It was revolutionary. But you can see that its collecting area really takes a nosedive even before we get to 10 keV. XMM Newton, which is ESA's flagship observatory, has a point spread function of about 15 arc seconds, more collecting area a little bit past 10 keV, but also takes a nosedive. Nustar at higher energies. Nustar is notable because at energies above 10 keV, it has a lot of collecting area. By the way, effective area means that we are considering the whole collecting area through the optic, taking into account things like reflectivities and those sorts of things, rather than the geometric area of the optic. It's the actual collecting, effective collecting area of the optic. So you can see that, when I put PSF 15 arc seconds, it's actually 20 arc seconds in the core and 50 arc seconds. So the PSF is a little bit worse, but it's the first time we've ever had a hard X-ray optic. I think I copied my label from XMM PSF, so that's a correction. It should be 20 arc seconds in the core, 50 arc seconds full extent. So we sacrifice a little bit because some of the technological challenges, we don't get quite as good of a PSF. Okay, so here's our next question. Which statement, so this is a quiz question, which statement about X-ray optics is true? So I'll give you a moment for your phones, your web browsers to load, and then I'll go ahead and read through these. So X-ray optics have already achieved imaging quality comparable to Hubble. And for those of you who know, Hubble does better than 1/10 of an arc second, just to give you a little bit of a clue. X-rays, the second one, X-rays must be reflected at very shallow angles along the sides of concentric shells. X-rays are absorbed into coatings and cannot ever be reflected. X-ray optics can only work at low energies. All right, so I'm checking our responses. Okay. Looking over on the iPad. Okay. All right, it looks like give people a little bit of a chance to respond. I can see that we've got responses still coming in, checking the app here. Okay, all right. It looks like we've got a comparable number of responses to the other ones. Okay, so it is indeed B. X-rays must be reflected at very shallow angles along the sides of concentric shells. All right, now we have one more question. And it is, I'll give you a chance to have it load up on your web browsers. My understanding of X-ray optics improved in the last. Watching the app come in. All right, great. I can see we've actually got most of the response. Okay, so some people already knew some stuff, so perhaps it was a little basic, but it seems like most people learned a little bit of something. Okay, thank you very much. All right, so why study galaxies in the harder band? So we want to study neutron star and black hole demographics, and this tells us about, to get specific, supernova explosion mechanisms. It is very hard to predict in supernova explosion models whether or not you end up with a neutron star or a black hole, given the complexity of supernova explosions and the end stages of stellar evolution, the second bullet point leading up to that point. So if we can actually tell you how many black holes and neutron stars we have in a galaxy, we can trace that to the star formation history and tell you about stellar evolution. We can also, as I mentioned, learn about the initial mass function. A second bullet that I want to mention specifically for hard X-rays is that when we study galaxies in hard X-rays, we have a chance at finding non-thermal emission that is attributed to particle acceleration in starburst environments. This is a very interesting topic, but I'm not going to be discussing it as much today. I'm going to focus on neutron star and black hole demographics. So now we're going to talk a little bit about the accretion states of black holes. And this is a body of information that was assembled over many decades by the Rossi X-ray Timing Explorer. Up in my the corner of my screen, RXTE, you can see the little inset with RXTE. So the Rossi X-ray Timing Explorer studied many galactic black holes over many decades, amassing a large amount of data. And from this, we have put together a picture of black holes going through accretion states. And to point at the graphic, when they are in lower states, the accretion disk does not extend as far inwards toward the center near where the black hole is. And instead, you get more of a corona, a hard X-ray corona, which the author of this particular review paper, Chris Doan, refers to as a hot, fluffy flow. And by the way, I think it's much better in her British accent than when I say it in my US accent. But nonetheless, you can think of it as that there's a hot, fluffy flow down in the center. We also see a large amount of hard X-ray emission when we're in a very high state. But interestingly, in a sort of high accretion state, but not super high accretion state, we see that the accretion disk extends farther down to the black hole, and we don't see as much corona. So we see black holes. This corresponds to X-ray spectra over here in the right hand. And you can see the labels according to which accretion state we're in. But what I want to point out, I don't want you to worry too much about this other than black holes go through accretion states. You can start to notice some things. If we look at the shape of the spectrum from 0.5 to 8 keV, which is what we would survey with Chandra, what we would cover with Chandra, the colors don't change very much. But if we go up to Nustar, very hard X-ray energies from 3 to 80 keV, you will notice that there's a very strong change in the X-ray colors, the X-ray spectrum, that is, the anticipated X-ray colors in this harder part of the spectrum. So this means that we're able to differentiate based on the shape of the spectrum. We expect to get different colors. We can tell something about what type of object, what kind of state it's in using the hard X-rays. So this is something we've been developing over the course of the last 8 to 10 years working with Nustar data. My colleague Andreas Zessas has been instrumental in putting this together. And we start to find, based on, now this plot is based on thousands of observations of Milky Way X-ray binaries with RXTE that have been translated into the Nustar bandpass. These are Nustar count rates, which have been normalized to the same distance. You can kind of think of it as a magnitude, but it's a normalized count rate. And then a color in these two bands, 4 to 6, 6 to 12. You can see that we start to trace out these distinctive areas where pulsars, and by the way, there's a question coming about this. So just notice that the pulsars trace out a distinctive region from the black holes. And so we can actually tell something about what the compact objects are by looking at the Nustar colors. And if we can take the hard color and the soft color, extending all the way up to 12 to 25 keV, then we start to see that things really separate out. So here we've got the pulsars. And by the way, pulsars, of course, are very high magnetic field neutron stars, whereas we have the low magnetic field neutron stars, which we've labeled it as neutron stars. And you can see that all of these objects are tracing out distinctive regions within parameter space. Okay, so we can use this diagnostic tool to learn about populations in galaxies. So now we've got a quick question, so I'll give you a chance to load up your web browser. Which statement about black holes is false? So you can look at this. I'll give you a second to let your questions load. And all right, I'm just making sure the app is loading. Okay, so I'll read through these as you get your web browser up. So you probably need a moment to get through these. So stellar origin black holes may undergo a state transition during which the relative intensity of the accretion disk and corona change. Pulsars occupy a distinctive region of hard X-ray color space. The X-ray colors of black hole binaries are identical at energies below 10 keV and energies above 10 keV. And the X-ray colors of pulsars are distinctive from those of lower magnetic field neutron stars. All right, I can see the responses coming in. All right, interesting. And you can update your response if by any chance you change your mind. Okay, which I think I saw actually happening in real time. Okay, it looks like we've got most of our responses are in. Okay, one or two more other people. Okay, so it was indeed C. The X-ray colors of black hole binaries are identical at low and high energies. The X-ray colors are quite distinct, okay, at low and high energies. And A was actually true. Stellar origin black holes do undergo state transitions. And I did say may because they don't always undergo state transitions, but they may undergo state transition. And the accretion disk and the corona intensity does change. So I'm going to actually go back and just show you. So this figure here in the lower right corner shows the relative intensity of the accretion disk and the corona changing based on the accretion state in black holes. So that is actually true. Okay, so we're going to move on to some actual data on Nustar observations of galaxies. So I like to start off with the M31 Nustar Legacy Survey, which is approximately a megasecond of observation time. So you can see the cutout of an ultraviolet image of the that is a Galax ultraviolet image of M31, and you can see the corresponding Nustar hard X-ray data. So just to remind you, the core of the PSF is about 20 arc seconds. The full PSF is more like 50 arc seconds. We've detected quite a few sources in M31, and we've published several papers, which I've listed here. I wanted to advertise two papers I can't focus on as much right now, but there's a very hard X-ray source near the center of M31, which we nicknamed Mihoko X1, after Mihoko Yukita, who wrote a paper about this. It's probably a pulsar, a previously unrecognized pulsar. And then we also had a paper by my colleague Tom Macaron describing the X-ray sources in globular clusters. And this was very interesting because there's a lot of study about whether or not black holes can survive the N-body interactions in globular clusters. And I encourage you to go read this paper. It turns out that many of these sources are indeed consistent with being neutron stars as well. But we're going to look at the whole population here. So just to orient you, this is the same kind of color diagram that we were looking at before. Now it's got actual data. Now I need to be honest with you and point out the typical error bars here. Okay, see that big cross? The error bars are actually pretty big. This is the first ever imaging hard X-ray telescope. And as I'm going to describe to you later, we have plans to build future hard X-ray imaging telescopes, which will have better imaging quality, better collecting area, better sensitivity. But this is the first time we've ever been able to do this sort of measurement. And we can see that there are trends that we don't find data that are consistent, very many data points that are consistent with black holes, just a small number. And some of these points up here we actually think are background sources. Most of the sources in M31, which is a more evolved population, are consistent with being neutron star binary systems. And we can actually then look at our identifications in the hard X-rays. For instance, I'll draw your eye to the pulsars, okay? So you can see these magenta points. And we found it to be very interesting, and this is analysis is undergoing, that is ongoing right now, that the pulsars tend to trace the spiral arms of the galaxy, which is where we know that there is more star formation. So it's a very suggestive and interesting thing that the pulsars are actually tracing the spiral arms of the galaxy. And in this case, we have a fairly high degree of confidence that those are pulsars based on their hard X-ray colors. Okay, so now I'm going to ask you a quick question about what I just said about the M31 study. So I'll give this a second to load up in your web browser again. Again, polev.com/Hornschemeier074. Hopefully you've kept it open. So I'll go ahead and read it and give you a second to think. Which statement is true concerning black holes and neutron stars in the Nustar M31 study? More neutron stars were found than black holes. More black holes were found than neutron stars. The number of black holes and neutron stars are about the same, or none of the above. And the responses are already pouring in. Okay, so I'm looking at my app over here on the iPad. All right, I can see the responses ticking in. And it looks like, okay, I'm going to go ahead in the interest of time. Good job, audience. A is actually the true one. More neutron stars are found than black holes. Okay, so I'll go back and just show you this. So this color diagram, if you can see the neutron star region, and I admit it's a little bit of a trick because I didn't put the neutron star label. Z and atoll sources are neutron stars. Pulsars are neutron stars. We actually don't find as many black holes. Okay, so looks like that point got across pretty well. We've got one more question that's actually more about you than about this talk. So a question about your research. So I was just talking about very local galaxies, but I'm very curious about my Valongo observatory audience. And I'm curious about your research. What kind of objects? So, okay, you're already answering whether you study with objects within the galaxy, within the very nearby universe, or the high redshift universe. All right. All right, so I can see that the answers pouring in. Okie doke. All right, so it looks like this is very interesting to me that we've got it looks like almost even split between people who are studying sources within our own galaxy and those that are studying objects within at intermediate redshifts. So, okay, so we've got a mostly galactic group here. Okay, that's very interesting. Oh, it's getting more galactic as time goes on. Okay. Okay, thank you. Very interesting. So I want to give you a little bit of information about the wider sample that we have studied with Nustar. So in addition to studying M31, which is obviously one of the very nearest galaxies, we've also studied a broader sample of galaxies. And here I show a plot of star formation and stellar mass with lines of specific star formation rate to give you some idea. And here's the Milky Way, which is it's sort of quiescently star forming in the grand scheme of things. And you can see more star bursty type objects like M82 up here at higher specific star formation rate. These are the galaxies that we have surveyed so far with Nustar. And I want to point out that these lower mass galaxies at lower stellar mass, Holmberg 9, Holmberg 2, NGC 1313, NGC 5204. These galaxies, by and large, were targeted because they had an individual luminous X-ray source within them. But Nevin Vulik, who is the author of the paper on these 12 galaxies, looked at the entire source population within all these galaxies, regardless of why they were targeted. So this is another plot of our sample, just to give you an idea. Of course, M31, this is point source sensitivity versus distance. You may recall I showed you a plot at the beginning of the talk of all the sources within our galaxy above 10 to the 38. So we can do a little better with Nustar. We get down to the few times 10 to the 37 ergs per second luminosities, but that gives you some idea. M31, we can get down to 10 to the 36 ergs per second. Most of our galaxies are between 3 and 5 megaparsecs. So this is what happens when you look at a dozen galaxies and analyze all the X-ray sources. And again, our error bars and limits are somewhat significant, but we find 128 individual sources that we can identify as black holes or neutron stars, either accreting pulsars or low magnetic field neutron stars. And then we can start to do interesting things with these sources because we can split them statistically as to whether or not we think they are black holes or neutron stars. So here we show a plot in two different bands, 4 to 25 keV and 12 to 25 keV. So the harder energy, 12 to 25 keV, is the blue, and the wider band, 4 to 25 keV, is the black. So what this is the black hole fraction, the fraction of sources that are black holes as a function of point source luminosity. And there will be a question about this later, so just to help you out, I hope you will notice that overall, the fraction of sources that are black holes goes up with X-ray luminosity. So that means that as you get to higher X-ray luminosity, you have a higher fraction of black holes. Sources are more likely to be black holes. One interesting thing that we found was this little dip in the black hole fraction in the full band, 4 to 25 keV. And it could be, so if it's a lower ratio of black holes, that means there's more neutron stars. So we suggested that possibly there was a clustering around close to the Eddington limit for 1.4 solar mass neutron star. It's just a suggested, interesting possible result. And this is the type of thing that should very much be improved with future hard X-ray observatories. We can start really getting into what fraction of the sources are neutron stars and black holes. This is a parameter that is of great interest to theorists. Okay. So we can look at galaxies, resolve the individual point sources like we did in that study. We can also look at the total X-ray emission from galaxies by studying the X-ray spectral energy distribution. So an excellent example of this sort of work is conducted by Kristen Garofali. I should say Kristen and Nevin Vulik, who I mentioned before, are in the group at Goddard. Although we're distributed geographically a little bit because of the pandemic, of course, but we're all at Goddard, associated with Goddard. So this is a low metallicity starburst galaxy, VV114. And you can see here intensity contours with Nustar. So we're not able to very well spatially resolve with Nustar the hard X-ray emission from this galaxy. But we can still, using a combination of data sets, Chandra and XMM help us to get at the softer X-ray emission to look at compact objects and hot gas. And then we can also use Nustar to look at compact objects at higher energies. So this is what happens. There's actually theoretical prediction for what the spectral energy distribution of normal galaxies should look like in the X-rays. So you can see down at low energies, these are, so 0.5 to 1 keV or so, these emission lines are models of what we expect the hot interstellar medium, all the elements in the hot interstellar medium how they would be emitting. At higher energies, you can see it's a much cleaner sort of broken power law type of spectrum because the spectrum is very much dominated by X-ray binaries. And isolating these two components really requires that we have a very broad band pass so we can sort of cleanly sample the hot gas and cleanly sample the binary, accreting binary part of the spectrum. So Kristen Garofali has done some analysis of several galaxies that are very well observed over this entire band pass. And the interesting thing is, and I should have pointed out that as we go to lower metallicity, as we expect, theoretically, we expect the X-ray emission from binary systems in particular to be elevated. And the reason for this is that as the metallicity goes down, winds become weak. And when there is less stellar mass loss, because the winds are weak, more mass stays with the compact object. So you expect to get more black holes and possibly heavier black holes. And black holes tend to be more luminous. So this all leads to that lower metallicity means higher X-ray luminosity. So does this bear out with the data? These are theoretical predictions. So these are now model fits to actual X-ray data. And we have a set of 3 galaxies, 3256, 253, and M83, that all are around solar metallicity. And you can see that they line up pretty well. And then if we add VV114, which I just showed to you in the previous slide, it's at half solar, and it lines up pretty well with the theoretical expectations. And then if we look at a very metal poor galaxy, NGC 3310, it also has very low metallicity. So what are driving these galaxy to galaxy metallicity? So variations. So metallicity we think is about 0.9 dex, but we do expect some statistical scatter from galaxy to galaxy, and we also do expect that stellar population age will affect things. Okay, I'm pausing for a moment. Okay, all right. So I'm seeing some comments on on this. So, okay, and I just want to pause and I'll catch up on a few questions that I think were related to the previous part of the talk. I got a question about why the error bars have the high values. That's a very good question. Thank you. So the reason that they have high values is there's a couple reasons, but one is that our PSF is not very good. So this is an imaging hard X-ray telescope, but we still have some source blending between sources, which contributes to our error bars. And also, to be honest, this is a relatively low collecting area telescope, so we just don't have quite as much signal. So statistically, we don't have a large number of photons in every single one of these sources. So those two things contribute to us having pretty large error bars. And I will comment on the next generation of missions. Don't worry, that's coming. So I think I'm caught up on the chat. I want to remember to look at that. Okay. Okay, so I went through this plot and explained the statistical scatter, and I'm going to want to explain why this is so important. So it appears to be that our observations in theory are both telling us that at lower metallicities, galaxies are producing a lot of additional X-ray emission, and that particularly we can see that the compact objects are producing a lot of X-ray emission. And this is why this is important. If we go back to earlier times in the universe, which we call the epoch of heating, and this is above redshift 10 at very early times in the universe, the high redshift X-ray galaxies, they are metal poor galaxies. And there's an open question about, can these types of X-ray binaries heat the intergalactic medium in the early universe? And I want to point out that Kristen Garofoli and Antara Bazuzak in our group both work on this quite a bit. So it appears to be that X-ray binaries are a dominant form of heating in the early universe. So these are now, we're looking at high redshift galaxies. I've changed topics a little bit here, but these are predictions based on supermassive black hole X-ray emission, how it should behave over cosmic time, getting up to high redshifts. You can see that it's really going down around the epoch of reionization, whereas galaxies we expect to behave in this way based on the evolution of galaxies. And the interesting thing is if we extrapolate to redshift 10 to 20, we find that we expect the lower mass black holes and possibly neutron stars in galaxies, low metallicity galaxies, to be the dominant source of X-ray emission that might heat the intergalactic medium. Okay, so I'm just pause and give you a moment here. Now, if the X-ray emission from very low metallicity galaxies was even more or not very well understood, then we wouldn't understand this very well. So something we're working on is really trying to find good local universe analogs for these high redshift galaxies to understand their X-ray emission. Okay, so I've got another question coming up. So get your web browser ready. There'll be two questions in a row. One will be a very easy one. This one's perhaps slightly more difficult than the next one, which is very easy. So letting your web browser load, and I'll open up my app. Okay, so when we observe galaxies with Nustar at high energies, which statement is false? The more luminous the point sources, the more likely they are black holes. The higher the metallicity of the galaxy, the higher the X-ray luminosity. Lower metallicity, I may have given something away with my tone of voice. Lower metallicity galaxies have higher X-ray luminosities. In a sample of 12 galaxies, approximately 128 neutron stars and black holes were detected, or none of the above. Okay, so I'm just looking at the responses on the app to give people a chance. And we've already got a fair number of responses, and you've all got it. The higher in metallicity of the galaxy, the higher the X-ray luminosity. That is indeed the false statement. We expect lower metallicity galaxies to have higher X-ray luminosities, and that's what we observe. Okay, now this is just your best guess. So I told you that this was an inexpensive mission, and I'll just give you the reference point that the James Webb Space Telescope is more expensive than $8 billion. So that's the perspective I want to give you. I know this isn't pocket change, but anyway, what would be your guess at the cost of the Nustar Observatory, not including the launch vehicle? That would be the rocket. So you just have to pay for the spacecraft and the telescope and the instruments the actual spacecraft itself. You don't have to worry about the rocket or the launch vehicle. So what would be your best guess? All right, giving people a chance, and got the responses coming in. All right, so, oh, this is very interesting. So, and give you just a second. And I can see that a couple of people are changing their responses, which is very interesting, the interaction. Okay, all right, I'm gonna go ahead and tell you the answer. So Nustar actually cost around $120 million. So it was a small Explorer mission. It's the smallest category of Explorer missions that NASA launches. So it's considered to be relatively low cost in terms of NASA missions. But I appreciate those that said $150 to $200 million, because I think it's worth much more than $120 million. But that'll give you some idea. So I'm going to set you up with what we're expecting in the future. So we're actually studying follow-on missions to Nustar. And there are two concepts currently, and I won't go into details, but if you want more information, I'm happy to talk about it at the end. So FORCE is a concept that's being led by Japan, and HEXP is a concept that is being led in the US. So FORCE you can think of as Super Nustar with a 12-meter focal length, and you can see this is a concept of what we think HEXP would look like with a 20-meter focal length. And HEXP would actually have 5 arcseconds angular resolution and 10 times the collecting area of Nustar, and would probably cost in the many hundreds of millions, probably, I think very safely under $1 billion, whereas FORCE, we think, would cost probably in the range of $120 to $150 million. And it's a little bit hard to say because you have to translate Japanese and US dollars. But with either of these missions, with better angular resolution, this is actually showing 15 arcseconds angular resolution. You can see what we were able to do with Nustar and then what we could do with HEXP and FORCE. We can detect many more point sources with greater sensitivity and really push this neutron star and black hole science. Okay, so now we're going to change gears, and in the last couple of minutes, I'm going to talk to you about wide field surveys. We're switching topics from hard X-rays to wide field surveys. And as I get into this, I want to acknowledge the work of Antara Bazuzak, has really led this effort to make predictions for the E-Rosita All-Sky survey. So I need to tell you that I am an external collaborator. This is a project that is very much being led by, the instrument is a German instrument. It's on board a Russian spacecraft. And right now, they're actually planning a major press release for a Nature result, which I could not talk about because it's embargoed, but you should just keep watching the archive and for press releases coming out of E-Rosita. But we made some predictions about what we expect to see with E-Rosita. I cannot help but share the following image before I get into the actual mission and our predictions. So this is 6 months of E-Rosita All-Sky survey data, which is publicly available on the web. This is a beautiful image of the X-ray sky, and it's only the first 6 months. They will be conducting an all-sky survey over 4 years. And you might be wondering what all these various objects are, but this gives you some help. So you can identify some of your favorite astronomical objects. Since half of you studied the galaxy, I'm sure you have some very, very much favorite objects down here. Some very large supernova remnants that will be very well studied by the all-sky survey capabilities of E-Rosita. I did want to point out that if you see an object here and you want to work on it, you need to pay attention to which part of the sky it's in, because the Germans and the Russians have split the sky. So if you want to work on anything on this half of the sky, you work with the Germans. And if you want to work on this part of the sky, you work with the Russians. We are collaborating with the Germans on our work. Okay, so this is the first all-sky X-ray survey in a generation. And it launched on July 13th, 2019. And at this point, I I can't help but say that this was a happy birthday event for Thiago, who's I know on the staff at the observatory. So it was a nice happy birthday present to Thiago to start the first X-ray all-sky survey in a generation on July 13th, 2019. So eROSITA is a mouthful, the extended Röntgen survey with an imaging telescope array. German X-rays or Röntgen rays in German. So there are 7 co-aligned telescopes, and it's the first all-sky survey in a generation. ROSAT surveyed the sky in the late 1990s, and ROSAT did not have any capability to look even above a couple keV, so it's the first ever imaging all-sky survey in the 2 to 10 keV band, and it surveys the full sky every 6 months, and over 4 years it'll do 8 scans. It's got a simultaneous field of view of 1 square degree. Okay, so I'm going to do a couple more slides, and then I'm going to check the comment field just to make sure that everybody's okay. Looking at some. Oh, okay. I see. Yay me. Okay, so Thiago heard me say happy birthday for the launch. Okay, I think there's no questions that I'll address right now. But moving on. So this is actually a plot that Peter Pradell, who was the eROSITA PI until shortly after launch, made. And it shows not every, but a pretty comprehensive set of X-ray missions that operated previous to the eROSITA launch. And you can see that in the early days of X-ray astronomy in the 1970s, there were hundreds of sources, maybe 1,000 sources when we launched the Einstein Observatory in the 80s. And then as we got into the 1990s, this is the ROSAT all-sky survey, gets up to 10,000 sources, Chandra and XMM, number of X-ray sources detected per year. You can see it rising. Here is eROSITA, but hold on. This is what we expect, which is a revolution with eROSITA. At the end of its first year of operations, eROSITA will have detected as many new sources as have been cataloged in 50 years of X-ray astronomy. We joke a little bit in X-ray astronomy about how we just don't have the statistics at like in optical or UV astronomy, with surveys like the Sloan Digital Sky Survey and other large surveys. This is really going to be a game changer in terms of the statistics of the X-ray survey. And I know I'm running a bit over, so I will try to finish up here pretty soon. So I think I'll skip over this, but you can refer to it later when you look at the recording. It just shows where eROSITA surveys fill in with respect to current surveys. So we expect in the science for the eROSITA experiment focuses on clusters and AGN. So mapping the structure of the energetic universe. They expect to find 100,000 clusters of galaxies and approximately 3 million AGN. But there's a lot of other stuff we're going to find in the survey, the very bottom of my slide, like normal galaxies. So what we have done with Antara Bazuzaik, and again, I'll be stepping through this a little quickly, but we've taken the Hecate catalog, which is work by Konstantinos Kavlakas, a graduate student who's defending his thesis very soon in Crete. He assembled this galaxy catalog of approximately 75,000 galaxies with Sloan, Galax, and WISE information, as well as IRAS data. So we have star formation rates and stellar masses. We focused on galaxies in the 50 to 200 megaparsec regime because these are galaxies we expect to appear as point sources in the eROSITA data. It has about a 20 arcsecond PSF, again, over the entire sky. So we took these galaxies with star formation rates and stellar masses, and we took existing relations between X-ray luminosity and star formation rate, between the X-ray binary, the hot gas emission, X-ray emission, and the hot gas temperature, and then also the amount of X-ray emission for star formation rate that you expect for hot gas. We took all of these relationships, put them together, and made predictions in Bazuzaik et al. 2020, which is available and published. So we can actually then make predictions using the effective area of the eROSITA experiment, the anticipated survey exposure over the skies. So there are, of course, regions of higher and lower exposure. And we can also take the background, the anticipated particle background. eROSITA operates at the L2 Lagrange point, by the way. We can take all of this together and predict whether or not galaxies are going to be detected. All right. So we've done this. And here is the parent sample, 75,000 galaxies. I'm sorry, the axis is a little bit cut off, but it peaks at about 5,000 galaxies per bin, and down here is hundreds of galaxies. So we put all of these galaxies in, did simulations, and we worked out that 15,000 galaxies are expected to be detected over the entire sky. And if you do big galaxy surveys, that might not sound that impressive, but in the X-ray band, this is very impressive. The previous Rosat All-Sky survey detected about 198 nearby galaxies. It just didn't have the sensitivity to detect normal galaxies. We expect, based on our simulation, that there will be a large population of early type galaxies, but that's very much sensitive on what the hot gas properties in those elliptical galaxies are like. For context, we have shown a plot. This is from Bazuzaik et al. 2020. Samples of nearby observed galaxies with Chandra and XMM. High redshift surveys. So high redshift surveys typically find samples in the tens to hundreds of galaxies. By the way, there's a question coming about galaxy sample sizes in the X-rays. So just note that we're talking about tens to hundreds, maybe a couple of hundreds of normal galaxies detected in previous samples. And by the way, we're not talking about AGN, we're talking about non-AGN galaxies. Okay. But this shows you the region of parameter space at sort of intermediate distance, intermediate luminosity that we expect to be filled in by E Rosita. So this will be very exciting in terms of statistics. So my next question is, before E Rosita, how big were normal galaxy samples detected in X-rays? So I'll give you a second to load up your browser. And we only have a couple more of these questions left. And this will be my chance to also remind you that at the end, I'm going to ask you about your favorite part of the talk. So if you got distracted, I'm making sure you know about that now. Okay, so here we go. The answers are starting to pour in. Okay, we've already got several people who've answered A. So it's tens to perhaps a couple hundred, thousands of normal galaxies, hundreds of thousands. All galaxies everywhere have been detected in X-rays. And I was getting a little bit punchy when I started writing this one. Okay. Okay. All right, looking at the total rack up of responses, it looks like we're getting close to the numbers that we had on the previous question. So I'll give it a couple more seconds. All right, so the correct answer is A, tens to perhaps a couple hundreds of galaxies. And this is, I'm referring to detections. There have certainly been statistical studies of undetected galaxies, stacking analyses, those sorts of things. But actual detections of normal galaxies, the sample sizes have been relatively modest up until now. Okay, so I'm going to close by telling you a little bit about a mission that we're studying at NASA. The PI is Will Zhang, who I showed earlier in the talk as having been the one to produce the glass for the Nustar mirror. But we are working on a Star-X, mission called Star-X, which would be a wide field of view. And here you can see the fields of view of various X-ray missions, including E Rosita, which is close to a square degree. Star-X would have 1 square degree. This shows you the collecting area of Star-X compared to other missions. So it's not quite as high as E Rosita, but it would have a 2.5 arcsecond angular PSF, that is 2.5 arcsecond PSF in the X-rays, which will be much better for imaging, and a simultaneous UV telescope. And this is probably not going to be an all-sky survey mission, but should be able to quickly survey tens of square degrees because it'll have very fast slewing capability, and will be able to build up over the course of the few years of its prime mission, build up perhaps hundreds to thousands of square degrees for variability studies in the X-rays. One of the things that we will get for free out of this will be an excellent normal galaxy sample. And again, this is a mission that's at relatively modest cost, around $250 million. So one slide after this, which is just what is the favorite part of your talk, and then the conclusions. So this is a little bit, you can refer to this later, but Star-X will be excellent for following up on gravitational wave sources, because it will be able to scan the expected error bar that is expected in the year 2024 with LIGO, Virgo, and CAGRA. And it'll also have a UV telescope for finding counterparts. So I'll let you refer to this later. Okay, so last polling question before we open up the questions. What was your favorite part of the talk? So this is going to be a little different than the previous ones. You can type something in, but then if you see something that somebody else types and you want to vote for it, you can do a like or an upvote option. So somebody will have to start typing something, and then the rest of you, if you like, you can vote for as many things. Okay, great. So we've got one, scientific instrumentation. Okay. So I'll give you a second because this is a little bit different than the previous questions, that you might want to respond again and uptick other people's responses. So we'll give this a few more seconds. And I apologize to Luan for running a couple minutes over, but I just have my conclusions chart and we'll be done. Okay. Nice. So I love that great panoramic view of X-ray astronomy. All right, great. I'll try to keep my day job. Thanks. That was a nice comment. All right. Scientific instrumentation. Really enjoy the forecast of Eurysida. Okay. Science prospects with Nustar, imaging of nearby galaxies. So we need to give people a chance to type on this one. It's not quite as simple as just clicking. Okie doke. All right, I'll give it 10 more seconds, and then I think we're gonna go on. Okay, great. So I appreciate this feedback, and thank you very much. So I'll just go ahead and put up my conclusions, and I'll prepare to get over. I think actually, Luan, you told me how the questions are gonna work, so I'm prepared for that. Okay, conclusions. With Nustar, a low-cost mission, again, $120 million, we've been able to separate neutron stars from black holes and determine well the overall X-ray spectral energy distribution of galaxies. A follow-on to Nustar could be FORCE or HEXP at lower moderate cost. With eRosita, a medium-cost mission, by the way, I didn't mention a cost, but I can explain why, but it's a European, German, and Russian mission. So the entire sky will be surveyed, and the largest population yet of normal galaxies will be detected in X-rays. And a follow-on to eRosita could be STAR-X, which can survey very wide fields at low to moderate costs. Okay, so I will just leave this up here. You can feel free to email me or check out our group's webpage. And with that, I guess Luan will open the floor to questions.
Okay, thank you for this great overview, and I really learned a lot, especially because I do not work. I work with exoplanets, so for me that was really interesting. So thank you very much. We can start with a fair request from Thiago, right? So he wants some reduced data as the birthday present. So I think it's a nice request, right?
Well, I think by your next birthday, Thiago, we can make that arrangement, because right now the eRosita team's planning a paper splash prior to March 2021. That's when they'll have their first data release. And by the way, I'm now looking at my iPad instead of my computer, but they plan a big paper splash around March. And so some data will start coming out. Right now, the data access is rather restricted because they're still in the early phases of the mission. But I think this is totally reasonable by July 13th, 2021.
Okay, so let's keep on Thiago's comments and questions. So he asks, he says that what we were talking about, so hopefully you can visit us in person in the future. But for now, he asks, how could X-ray binaries also affect reionization?
This is a great question, Thiago. And the answer is yes, this is possible, but all the research to date indicates that at that time, around reionization, supermassive black holes are probably the stronger source of X-ray emission relative to X-ray binaries, so probably would play a more important role. So, and I think as we get into the epoch of heating, we're sort of running out of a large number of different types of sources that could possibly be doing the heating. So that's part of why X-ray binaries become a more significant prospect during the epoch of heating. It can play a role, but current studies indicate it's probably not a strong contributor. But we should continue to study the X-ray emission from low metallicity galaxies to understand this better.
Okay, thanks. So I'm just gonna show this, and because you answered that during your talk, but just to let Yana, if you think that there was some aspect that you wanted to learn about future missions that maybe was not mentioned, so please let us know in the comments, okay? But I think that Anne gave a nice overview of the future missions, right? Oh, do you want to add something in?
Yeah, I can just say that we're actively working on force. And so in either of these cases, by the way, NASA Goddard, where I am and where Will Zhang is, would be providing the optics. So we're doing technological development, and maybe for some future talk, we could have one focused more on that. But we're very much working on the optics and the hard X-rays, because that's really our limitation. Our detectors are in pretty good shape, but we have a lot of work to do on the optics, particularly the multi-layer coatings to reflect the hard X-rays. But that's something we're working on for both of those concepts. But sure, if there's additional questions, I can answer them.
Okay, thanks. So another question from Thiago. So he assumes that OB populations would be brighter in the UV, but maybe the XRBs contribute somewhat. So can you comment on that, please?
That is a great question. So I think we're talking about the epoch of heating in the early universe. And what is most relevant, and this is work that Antara Bazuzak and Andre Messenger and others have been working on. It's the softer X-ray emission for the heating in the intergalactic medium. And you're right, you don't expect as much UV emission from certain categories of X-ray binaries. They really confine most of their emission to the X-ray bandpass. But in the softer X-rays, there is, depending on the properties of the intergalactic medium, this possibility that the softer X-rays, and when I say soft, I mean around 0.5 to 1 keV soft X-rays from black holes and neutron stars. Those are the X-rays that we think might be heating the intergalactic medium. But you're right, there isn't necessarily as much ultraviolet emission coming from those systems.
Okay, thanks. So, by the way, you mentioned the hard and soft X-rays, and I was remembering the plot that you showed with the different populations. So I come from an exoplanet background, and whenever we show the mass versus period plots, we know that there are some biases there. So when you show these plots with the populations, so the regions that don't have any objects, they actually we will not expect to find objects there, or there may be some biases there in the detections.
Those are great questions. At first, just a general note that soft and hard X-rays is just saying lower and higher energy. So one always needs to be careful about what the definition is. And during my talk, I tried to define what I was talking about. But just in general, if an X-ray astronomer says those things, you should check about what bandpass they're talking about. Okay. But with respect to the point sources, so that's a great question. We have some confidence based on decades of observations of galactic binaries and Magellanic Cloud binaries as well by the Rossi X-ray Timing Explorer. We have a fair amount of confidence about the regions of parameter space that we find black holes and neutron stars in. That said, there have been surprises. And something that I didn't mention during this talk, which is frankly, for me, I think one of the most exciting things that's come out of Nustar is the discovery of ultraluminous pulsars. So these are pulsars that apparently did not read our physics and astrophysics books because they emit, at 10 to the 40 ergs per second, sometimes 100 times the Eddington limit of a neutron star. But we found pulsations with Nustar, and a lot of credit goes to Matteo Becchetti, who's the author on the first paper on this particular topic. But since this happened, we found more. So certainly when we start looking at other galaxies, we start probing parameter space that we haven't probed within our galaxy. I think we've got a fair amount of confidence about the regions in those diagrams because of decades of observations in our galaxy. But you're right, Luan, that one should always ask the question and continue checking.
Okay, thank you very much. So talking a little bit about the surprising new stuff that we are studying. So Iana wants to know if the X-rays, the hard X-rays, can help us understand the mystery about intermediate mass black holes.
That's a great question. I think that hard X-rays can certainly help because we can pinpoint sources in interesting accretion states. But I have to be honest that with our capability in the hard X-rays right now, you would want to follow up with some other technique. And I think the best way to, for instance, get at masses in intermediate mass black holes, X-ray timing is a great way because there are quasi-periodic oscillations. You can actually search on this QPOs, timing signatures that correlate very strongly with the mass of the black hole. So what you really want is to do some precision timing or some precision spectroscopy to look at the accretion disk to make sure you really understand the temperature and structure of the accretion disk. And we X-ray astronomers also need to be honest that the best way to get masses remains to get an optical counterpart and to get orbital parameters. So some of the best work, for instance, Jerry Arose and others have dedicated their careers to doing optical spectroscopy. So we find the candidates in X-rays. So that is what hard X-rays can be good for. We can find interesting intermediate mass black hole candidates, and then we must follow it up. And optical spectroscopy to get orbital parameters remains an excellent way so that we can pinpoint the mass. So that was a lot seen, but these future hard X-ray missions should be able to find, because we have some timing capability, should be able to find candidate intermediate mass black holes. Probably will turn up large populations of them, but we'll need to work with our colleagues with other types of capabilities to verify them.
That's great, very exciting, thanks. So we have the next question from Mateus. So thanks you for the amazing talk. And he asks if Nustar can be used to study X-ray emissions of single hot stars' winds.
Okay, that's a great question. This is somewhat outside of my area of expertise, but I do know that there have been observations by Nustar of individual stars. So I know that there have been such studies. And of course, there's been a rich body. You asked about stars, but there's a rich body of observations of supernova and supernova remnants that have really been very helpful for understanding how elements are produced within stars. Because we can actually, there's certain heavy elements that radiate in the harder Nustar X-ray band, and we can actually read off of our plots what the metal production is in supernova to understand better stellar evolution. So I did not give you a direct answer, but I know that there have been some studies, and I'm not as familiar with that body of work.
Okay, thanks. And moving on here on the chat, so we have Karim. Thank you for the
Hello,
talk.
Karim.
And she has some questions and comments. So let's start here. Are the SED feeding tools that extend out to X-rays? So she's more familiar with extensions towards the far infrared.
Okay, that's a great question. So right now, we're still fitting our SEDs with our particular X-ray astronomy tools, but something we're actually working on with some of our theorist colleagues, and I'm a big fan of this, is to, within a few years, try to get some of our binary population synthesis codes. And I'm not a theorist, my colleagues are theorists, but there is some plan to get the next generation of binary population synthesis codes available perhaps on the web, so that people can generate X-ray spectral energy distributions of binary populations in a manner similar to some of the tools that have been around for quite a while in optical and UV. But right now there isn't perhaps an easy tool. You'll have to find your favorite X-ray astronomer perhaps and work with them. But I know that Corinne, she has several favorite X-ray astronomers, but she has several that she can work with. But yeah, we don't have a tool that's that you would think of in that sense, like an SED fitting tool that's just widely available to everyone right now.
Okay, thanks. And so Karin's next question, I'm gonna put it's a two-part because of the comment limitation. So she starts by saying that you might have mentioned this because kids are there together. So when imaging nearby galaxies, are globular clusters bright because they are old and have higher frequency of stellar remnants? And then she proceeds by saying, on the other hand, I think effing star-forming knots will light up because of X-ray binaries. Color are then key to distinguish.
Okay, so there's a few things going on there, and I will note back to Karine that the reason I've got this headset on is because it was the lunch hour in the United States in Maryland, and I expected my child overhead and my dog to sound like a herd of elephants. So I have complete sympathy for that one. There's only 2 of them, but they make a lot of noise. Okay, so you had a couple questions. Are we able to go back? Okay, thank you.
Yeah.
So when imaging nearby galaxies, are globular clusters brighter because they are old and have higher frequency of stellar remnants? Okay, so this is a whole body of research, Karine, that is very interesting about whether or not the older X-ray binary systems are primarily formed in the field or primarily formed in globular clusters. And there is actually some thought that most X-ray binaries might actually be produced via n-body interactions in globular clusters. And then over time, globular clusters get destroyed and produce a field population. There's a whole body of work that I encourage you to look at. But it's very interesting as to what is the frequency of globular cluster X-ray binary. So it's not necessarily that they're brighter, but it is relatively common that we find X-ray binary systems in globular clusters. We find these neutron star and black hole systems in globular clusters. So it does tend to pop out a little bit when we look at the M31 image, for instance. We see some of our globular clusters detected in the X-rays. It probably popped out a little bit in that image in terms of looking brighter. So hopefully that... but yes, the age, stellar age certainly factors in, and you don't expect the older low mass X-ray binary systems, that is the systems that have a low mass star donating, they don't turn on until many giga years after star formation commenced. So you do tend to find those low mass X-ray binary systems associated with older stellar populations. Okay, so there was another question?
Yes.
On the other hand, star-forming knots will light up because of X-ray binaries. Colors are then key to distinguish. Yes, so those star-forming knots, we expect to have the high-mass X-ray binary systems. And I will point out that what we do to identify the neutron stars and black holes is great, but we like to work in concert with our colleagues who do Hubble analysis. And I want to have a little shout out to Margaret Lazzarini, who's finishing her PhD at University of Washington, Seattle, by the way. So she did a lot of work to look at the OB stars in M31 that were part of the FAT survey and link them up. So X-ray colors are key, but we still, of course, benefit from knowing about the Hubble stellar counterparts. We really use both. We want to know what the compact object is, and we want to know whether we've got a high mass young X-ray binary system or a low mass older binary system. So we use all that information to understand what's going on.
Okay, thanks. So Karin comments that she has lots to study, lots of new stuff to study. Okay. That's great. And also, Mateus, thank you for the answer concerning the massive stars. So that brings us. Let me check here if we. Yeah, I think these were the last questions. So that brings us to the end of this talk today. So I'll just want to take the opportunity to remind the audience that we talk a lot about black holes, and next week we'll have Kate Bauman talk about the first image of the black hole. So stay tuned for next week's talk. But as for today, I would like to thank you very much for this great overview. Lots of exciting results already, and more exciting results to come in the next few years. So congratulations for the great job you've been doing in the area, and thank you for showing us all these results to us. And it was a really interesting talk because of the interaction with the polls.
Yeah, I was gonna thank you all, and I do apologize for that taking a few extra minutes because one's never quite sure about execution time. But thank you to the audience for your participation because that made it more interesting for me. So thank you.
Yeah, those extra minutes were definitely worth it because it was really fun to interact during the talk. So before we end our broadcast, would you like to say any final comments? Okay, so we have here one for you. So Yanis says many thanks, and she wants more X-ray photons from now on. So. And Karin saying that Polev worked great, so people are commenting on that. So any final comments you'd like to tell the audience?
Oh, well, just thank you for attending. And I did have the privilege once years ago to speak at an SAB in Brazil, and I hope to return to Brazil someday. So I'm glad that we were able to connect this way, and I hope you all stay safe during the pandemic so that we can see each other again.
Okay, Anne, thank you very much. And thank you all in the audience for being with us in one more talk. So next week we have the last talk for this year. So stay tuned, stay safe, and see you next week. Bye-bye.